So, title of our first presentation this morning is a 5G network overview from Metro Edge to end user, presenting the 5G testing challenges poster walkthrough. So again, this goes back to when Jeff and I were first putting these seminars together, and we were discussing, what are the common challenges that his customers are running into, what are the challenges my customers are running into, and how they relate to one another. This is what spurred the idea of putting together this poster. Now again, this is what the poster looks like. You don't have to open it, but this is kind of an eyesore. But just to give you an idea of how this poster is laid out. What Jeff and I did, you work it from left to right. Left side of the poster here discusses the over-the-air measurements. So everything for both 5G NR standalone and 5G NR non-standalone, which Jeff is going to go into briefly in a moment. Then as you work from left to right, we start going into the transport side, everything from the front haul to the metro to the core network. And you'll notice each one has different requirements. The idea behind this first presentation is just to give you a brief overview of some of the challenges related to each one of those network segments. This isn't meant to go deep. This is just to give kind of the 10,000-foot perspective and frame what it is we're going to be discussing throughout today's presentations. So in this first part, I'm going to be handing this over to Jeff, and he's going to give a brief introduction as to what you can expect for the RF and over-the-air measurements.
I don't need that right now. I'll just use this one. All right. So when we're looking at the RF portion of it, there's two aspects, right? You've got standalone and you've got non-standalone. From the 5G perspective, it's the same. It's just a matter of what initiates the call or not. So standalone is strictly 5G, right? Everything basically originates and terminates from this UE, whether it's a fixed or a mobile. And if you want to advance the slide one more. But then when we look at non-standalone, right, we need the 4G support. And so as vendors roll out either non-standalone or standalone, there's going to be a potential need to have the 4G support. So if I'm in a particular location and I've got 4G and I'm turning up 5G for just my data backhaul kind of thing, or offload, then I set everything up in 4G. I want to make sure my signal quality looks good, because if it doesn't, then 5G will never work. So having an instrument that can support both the 4G as well as 5G from over-the-air perspective is very important for both non-standalone and standalone. And I'll get into more details as we go through my presentation. But that's all for the poster right now. Thanks, Danny.
So now as we're working, as Jeff mentioned, once we get over the air and we're now getting the signal to the radio, what I think it's important to discuss first is where we're at today as relating to 4G LTE and then moving into 4G LTE advanced and so on. It's important to understand where we've been so you can understand where we're going. So in the first part here, we're going to discuss briefly about what challenges we see at 4G LTE today, when everything from the deployment and specifically focusing in the mobile front haul aspect. So first off, what did this look like in first deployment? Well, yesterday's network, we'll call it that, we primarily saw high loss or heavy high loss coax going from that of the antenna on top of the tower, going down to dedicated equipment with high power consumption. There's your node Bs, there's your different power supplies and so on for your individual towers. All right. As we moved forward into 4G, we started seeing what is commonly referred to as DRAN or distributed RAN. Now what you're seeing is a transition where we had remote radio head units, or the RRH, that's being deployed on the tower itself. This is where it's terminating the RF signal, and then we're actually sending that data, the IQ data, over an optical fiber or a power feed down the tower to that of less equipment, lower power consumption at the base. Right? So we started to distribute those requirements. So instead of having all the equipment in the yesteryears of dedicated equipment on the tower, we started taking that of the remote radio head unit and then distributing that to the equipment at the tower, be it your baseband units. All right? But this was a one-to-one scenario. The radio head or the remote radio head communicating to one BBU or baseband unit dedicated for each site. All right? Now we move forward again to the third set And what we've seen now is going from a DRAN, a distributed RAN, to that of a CRAN, right? Which would be either centralized RAN or some call it cloud RAN. And now we've seen, instead of having just one dedicated BBU per radio head, we had more of multiple BBUs or BBU hotels, something of that nature, where you had that of multiple remote radio heads all feeding through a ring to that of a centralized unit. You would see these as CRAN hubs being referred to as, where you'd have a site that had multiple baseband units. Now, in each one of these cases, they were always being the communication that is carrying the IQ data from the remote radio head at the top of the tower down to either the individual baseband unit or that of the baseband unit hotel, was carried over a CPRI transport. CPRI stands for Common Public Radio Interface. And this has been a transport that's been used widely in 4G applications. Just a brief show of hands. How many of you are familiar with CPRI in the room? Okay, it's very common. Now, with CPRI, what was important about this was CPRI was primarily being not necessarily standardized. I don't want to use the word standardized because it didn't follow a specific standard, but it was a specification. And what I mean by that is this was done by the CPRI, it's held by the CPRI.info, or you can see it widely used by your common radio vendors, so that of Nokia, ALU, Samsung, Ericsson, all had CPRI support. Now what's unique about this, there was a couple challenges with CPRI. First of which, as you can see, there's a variety of different CPRI rates or line options that as you move up, you see that the data rates get pretty large. CPRI rate option 10 that we're seeing now for certain 4G deployments are supporting up to 25 gigabits per second. That's CPRI rate 10. Another challenge about this is that since it wasn't necessarily a standard, and what I mean by that, it wasn't an IEEE standard, it wasn't an ITU standard, this was done by a conglomerate of equipment manufacturers, each CPRI was a little bit different from the next CPRI. So what do I mean by that? Ericsson used CPRI, their CPRI protocol was different than that of Nokia's, and Nokia's was different than that of Samsung. So if your equipment, your radio equipment to that of your baseband unit, if they were both Nokia, you had no issues communicating over CPRI. But if you had Nokia and let's say Ericsson, you may have some challenges there because there's different things that are put in that proprietary, in that CPRI transport that may not communicate or interoperate with other vendor equipment. So although the term of its common public radio interface, it's a term used loosely. CPRI consisted of basically two layers. First layer is being that of the physical layer, the physical transport. And you've seen CPRI going optically over an SFP or an SFP plus interface. That's the pluggable optic that would be either plugged into that of the baseband unit, and the other pluggable optic could be plugged into that of the remote radio head. And then the fiber would connect the two together over the tower, over distance, depending on if you're doing a CRAN hub. That's either an electrical or optical transmission, and it can be either single mode or multi-mode fiber, depending on the distance and the bandwidth capabilities that was required to transport that CPRI. That was layer one. Layer two had a little bit more involved. This is more on the protocol side of CPRI, and that consisted of the in-band protocol. So this is where the in-band protocol is. That's where you had the differences between the equipment manufacturers because the in-band protocol with one radio vendor may not cooperate or interoperate with the in-band protocol of another equipment vendor. And then you had the IQ data. So there's all of your RF data that you would be able to analyze and be able to find things such as the presence of interference or PIM. You'd be able to see that within the RF signal. Okay? So how did we use this? So our customers came to us when they were installing these 4G sites and being able to test. What they were asking for is how do we verify that our CPRI protocol is working correctly, that we're able to communicate from that of the radio to that of the baseband unit Were we able to identify errors and alarms? If there was alarms that were being generated out of the equipment, be it the radio or the baseband unit, could we see that within the CPRI signal? Could we analyze that? And then finally, things such as correct SFPs from an optics perspective. Were we able to use the correct optics in both the ground as well as in the radio? These were some of the initial tests that we were supporting at 4G. Again, the reason I bring this up is because as we start talking about 5G in the upcoming slides, you're going to see a very significant difference in test requirements as we migrate into 5G. Before I move on, any questions with this so far? Is this making sense? Great. Now, let's talk about, now that we've discussed 4G requirements and what we've done in the past, let's talk about what we're being asked to support moving forward. And the biggest difference, first of which you'll notice that in 5G they call it XHall. It's not front haul anymore, it's called XHall. That's because XHall stands for one of three things: front haul, mid haul, or backhaul. Mid haul is the new introduction for 5G, and what we actually end up naming it, and you'll see this in later slides, you'll see NGFI 1 or 2. NGFI stands for Next Generation Front Haul Interface, and I'll discuss that in next coming slides. This is what's replacing your traditional front haul. Okay? You'll also notice that the requirements are a little bit different. You're going to see terms such as eCPRI and radio over Ethernet throughput. eCPRI and ROE, radio over Ethernet, is replacing CPRI. And I'll explain why. A lot of it has to do with when we start talking about the applications for 5G, we start talking about enhanced mobile broadband, which is a much higher bandwidth utilized requirement. It requires download speeds much greater than what we saw in 4G. And I mean, you'll see a lot of commercials today about, you know, this network supports this type of speed, and at 5G we were able to verify this. But we're still in our infancy stage at this, and we'll discuss how this is going to change and how eCPRI and radio over Ethernet play a significant role in this. You'll also see the introduction of network timing verification, and I'll discuss this in later slides as well. Synchronization becomes a much bigger test requirement in 5G than it was in 4G. That has a lot to do with the transition from FDD, or frequency domain duplexing, to TDD, or time division duplexing. And we'll talk about that later. So first, why change the NGFI for 5G mobile networks? What's wrong with CPRI? Why can't I just stay with CPRI? Why do I have to change to a new one? The big one has to do with, as you can see here, is the CPRI rate, the IQ rate, and the IP rate. So the IQ rate's always going to be there. The IQ is that of your RF data, right? That's not going to change. The biggest thing, though, is you'll notice, even as you get into higher CPRI rates, look at the IP rate. So this is your actual data throughput, your IP user data. You'll notice that even at nearly 10 gigabits per second, or CPRI rate 7, you only have an actual IP rate, end user rate, of 600 megabits per second, which only equates to an efficiency of 6.1%. So think about that. Out of your entire CPRI signal, your CPRI transport that is transmitting your data from your radio to that of the baseband unit, only 6% of it is actually IP data. When you start talking about the next generation applications for 5G, which Jeff and I both talk about, you'll see that that's very limited as compared to the applications. It's simply not enough bandwidth. How do we overcome that? And we'll talk about that moving forward. So what you'll see on the bottom here is that 3GPP created what's called splitting the Ethernet, or functional splitting. So here's the fundamental premises behind that of radio over Ethernet, or eCPRI. We're taking the traditional CPRI that we've talked about in the previous slide, we're turning it into packets, Ethernet-based packets. Not only are we turning it into packets, but we're able to figure out, depending on which type of split we choose, or how much data we want to include or not include in that packet, will determine where that RF data is being terminated. So what do I mean by that? You see on the bottom here with these options, the higher the option, the more that's being done at the baseband unit, okay, or away from the radio. The lower the option, the more amount in green you'll see that's being done here in that of the radio unit. So what you're seeing lately is that in 5G radios that are being introduced, they're putting a lot more emphasis on being able to process more in the radio, either through, like again, eCPRI or that of terminating that radio signal with the radio, and then putting the rest of the IP data over the backhaul to the baseband unit. What does that mean? In higher options here, more is being done in the radio, less is being done in that of the BBU, which gives you a 10 times greater throughput savings than that of CPRI. Why? Because that RF data is being done at the radio, not that of the BBU. Change to option 7, the higher rates here, you're seeing less is being done in the radio and more is being done in the BBU, and that turns into an increase of about 3 to 4 times bandwidth or throughput. Not as much as the lower options, but you're still able to get an increase in throughput. And you can see the differences, 7.1 and 7.2, that's relating to this here, reduces cost and impact to RRH because less is being done with the radio. However, when you see option 2, which is over here, it's an increased cost and complexity. Why? Because you're doing more in the radio, but you're reducing latency because all of that's being terminated in that, that's being done in the radio itself. So the question becomes, well, why do I want to do more in the radio? That's just an increase in cost. Yeah, I get better bandwidth utilization here, but it costs me more per radio. Well, when we start talking about applications that are latency sensitive, think about autonomous vehicles. That's always the most common one, the easiest one to relate to. Autonomous vehicles, or V2X, that's called vehicle to everything, requires a very low amount of latency for that traffic, when traffic being the data traffic, transmitting from your vehicle to your radio, back to your vehicle. Well, if I'm in a vehicle going 65 miles an hour on the expressway and it's an autonomous vehicle, I don't want to worry about my communication being buffered and going through a network. I want that going as quick to the radio and back to my car as quickly as possible, right? That reduces the amount of time and latency. That's where more processing being done in the radio becomes more effective. Now take another application, let's say weather monitoring. Weather monitoring, I don't need that to be as quick with latency. It's not going to be nanosecond changes in the weather. I can go with a different option where less is being done in the radio and more is being done at my BBU. I'll go more into detail on that in a little bit, but this is just kind of giving you a high-level summary of why CPRI is ineffective and why changing to eCPRI and radio over Ethernet gives me functional splits, thus giving me a flexible network. So who defines that next generation front haul interface? What standard bodies are responsible for it? Here I identified 3 IEEE organizations that have either defined NGFI or reference the NGFI within the standard. The first one is 1914.1, and they're responsible for the architecture. You'll see here, instead of calling it a baseband unit, they broke the functions up into 2 different applications. The DU, which is the distributive unit, that's where you're terminating your RF data, your IQ. And then the CU, the central unit, that's where it's sending out and distributing your IP data, your user data. Now in the past for 4G, this was all one unit, right? This was all the baseband unit. But in 5G, they're splitting the functions up and identifying them as NGFI 1, that's your front haul, and NGFI 2, that's your mid haul. Your back haul is still coming out from the CU here. Why is this important? Because once you identify this new network architecture, now you have different flexibility on where you want your traffic to go based on network latency, network availability, and network switching time. Moving on to 1914.3. This is what's defining the frame format. What does that radio over Ethernet frame consist of? So 19.1, architecture. 19.3, or 1914.3, the frame. And then finally, going down to 802.1 CM, this is talking about the synchronization of that network. And again, we'll talk more about that because that plays a bigger impact later. Yes, sir?
Is the difference between the protocols that you said of the different companies, is it because of the difference between the two, the NGFI 1 and NGFI 2? Are they splitting it differently?
Good question. So the question was, going back to this slide, correct me if I'm wrong, is the being able to split those different network elements up into the CU and the DU, is that to take advantage of these different splits, functional splits?
Are the companies doing it differently?
Are the different manufacturers doing it differently? Okay, so yeah, that's a good question. What you're seeing most companies do is that they're standardizing on what's called the ORAN. That's the Open RAN, and they're defining 7.1 and 7.2 as being the functional splits that are most desired. The reason they say 7.1 and 7.2 is because it has the best balance of both efficiency and throughput as well as low latency. At 7.1 and 7.2, you also have the best opportunity for interoperability among those vendors, which is what ORAN is focused on. The goal is to be able to have all of the equipment manufacturers work together in the same ecosystem and not have to have dedicated vendor equipment. But they do also have the functionality of creating different splits. So each manufacturer does have the flexibility to do so, and it really depends on the application they're supporting. In most cases, and we'll discuss this in later slides, you're going to see the same radio equipment support multiple splits simultaneously, and that'll be based on the type of traffic it gets. Does that make sense?
Yes.
Okay. Other questions? Okay. So, yes, sir? All right. Yep, no problem. So, why have these different subsections? Why break up the baseband unit into different functions? Well, the idea behind this, and as I mentioned this earlier, it gives you more flexibility as to where you need your IQ data to be terminated, how much bandwidth do you need for your data, and how fast does it have to get across your network. So you'll see a couple of different examples here. The colors being the green up here, that's your radio unit. Think of that as your remote radio head. The light blue is the distributed unit. Think of that as where you're terminating your IQ data. And the dark blue is the CU. Think of that as where you're sending your IP data out or your user data. Once you break this up into different functions, you have the flexibility of coming up with, in this case, 4 different scenarios on how my one site, cell site, or my 5G radio will handle different traffic. And again, it depends on what's being needed per that site. So for example, the very top one here, where the radio unit, distributed unit, and centralized unit are all co-located at the same spot. Think of that being very close to a DRAN today, where you have your dedicated BBU and your remote radio head all co-located together. This giving you the most expensive solution because you have to have dedicated hardware for each, but it gives you a very tight or critical latency value. So in this case, we even seen, I made that example about some radios that are now coming with the ability to have the basically BBU functions inside the radio. That would be an example of this today. Again, why would that be? Go back to the autonomous vehicles. I want my IQ data to be processed as close to the radio as possible for the least amount of latency. Then you start working down to the second one here, where I co-located just the DU and the CU. This is for ultra-reliable, low-latency communications. So here, my remote radio unit on the top, and then my CU and DU located together, but close to that of the tower, or close to that of the radio. Think of that almost like the DRAN itself. Then you see co-located just the RU and the DU here. This is for synchronization of antenna. So a good example here is of massive MIMO, where synchronization is key with the amount of radios that you're working with. And then down here, the last one, separate the RU, DU, and CU. This is the most flexible, most cost-effective, but what are you sacrificing? Well, now you're sacrificing latency, right? Now my latency, that traffic has to get all the way over here versus all being done here. So there's benefits and trade-offs to each one. How does this differ from 4G? In 4G with CPRI, you had no flexibility. CPRI was like a circuit. Once it was there, it was always transmitting. Whether there was anything in the antenna containers or not, it was always on. It always had the same latency. It was always very reliable because it was circuit-based. It was always synchronized. But what happens when you get higher bandwidth? You didn't get more IP data. You added more bandwidth, but your efficiency remained the same. This gives you the flexibility of differentiating those services. Okay, next part here is the precision time protocol network. This becomes a much bigger role in 5G as it was compared to 4G. And the reason behind that has everything to do with transitioning. In 5G, we're transitioning to time division duplexing. We're moving away from FDD and we're moving towards TDD. You also see applications such as coordinated multipoint, where multiple base stations communicate with a single UE or handheld device. Now, what's the biggest difference with TDD versus FDD? Well, FDD, you had different frequencies for your uplink and your downlink, right? You didn't have to worry about timing so much because, again, they were on two different frequencies. In TDD, they're on the same, but they're in different time slots. So depending on the time over that same spectrum, you're either doing uplink or you're doing downlink. You're not doing both. It's always at that specific time slot. So what happens here, and this is the example that we're showing on the left, is if you don't have good synchronization between multiple sites, one site thinks you're supposed to be on downlink, the other site thinks you're supposed to be doing uplink at that same time slot. So what happens? You have a phase misalignment, which causes collisions. This is when you start dropping service. This is when you start seeing degradation in your service. This is when you start seeing synchronization alarms. This is a very big challenge for 5D. There's a lot of benefits to it if you're synchronized, but maintaining that synchronization is key. Again, compared to 4G, synchronization was still required in 4G, but it wasn't as stringent as it is for 5G. And we'll talk about the reasons why. So how are base stations synchronized today? GPS, right? Most of us have GPS on those antennas or GPS at the sites and the big macro sites, or you're on top of a roof, rooftop installations and so on. Clear line of sight, no issues with GPS. Here's the challenge. In 5G, and let me know if this is new or if you've heard this before, in 5G, the whole idea is to get those radios to the street level, right? You're starting to see 5G on lampposts. You're starting to see 5G on traffic lights. There was a seminar that was held in New York about 2 or 3 weeks ago. It was sponsored by Light Reading. And it was right in Manhattan. And it was one of the presenters there, it was an equipment manufacturer, and they had a very interesting image. What they showed was, they showed basically Times Square. And in Times Square, they showed all of their 5G deployments that they're planning on putting on street level in Times Square. And it was amazing coverage. They were looking at putting 5G radios on nearly every street corner, every lamp, and they had a variety of them, again, traffic lights to lamp posts to even like bus stops, they were putting these things on. So the coverage for 5G was there. Then the next slide, they showed how many of those sites had GPS available. And it was a complete opposite reaction. You had all the coverage with 5G, no support for GPS. Why is that? Well, when you think about an urban canyon, you have these street lamps on the ground level surrounded by high-rise buildings. So what happens? You don't have that line of sight. You lose that GPS synchronization. Now you have to figure out a way to provide that timing at the street level without GPS. Another channel, and I talked about those first two, additional costs. That was the other issue they were bringing up. A service provider presented this during that same seminar, that they were talking about the amount of cost it would be to support GPS for every one of their 5G sites, especially with the small cells, how expensive it became. And they're like, it's not feasible. It just simply won't happen. And then finally, risk of jamming or physical damage. So how do we overcome this for 5G? We know we're going to TDD. We know we need synchronization, and we know that GPS is not going to be a viable solution, especially for street-level small cell deployment. What do? IEEE introduced what's called Precision Time Protocol many years ago. It's IEEE 1588 V2. This has been around for quite some time. It's nothing new. It's basically the ability of being able to take synchronization from a grandmaster site, so your reference point, and taking that timing and distributing that synchronization through your already existing fiber optic network. So think about this. Instead of having GPS at each one of your base stations, especially our 5G small cell, you're able to have one grandmaster site that's a clock receiving its master timing. This could be at a GPS site, distributing that in Ethernet packets through your PTP network to various base stations. A lot of advantages to this. First of which, it supports both frequency and phase. Why did we talk about how important phase is? Is because, again, if you have misalignment in phase with your timing, one site thinks you're transmitting, the other expects you to be receiving, you have misalignment there. So phase synchronization is important. Grandmaster distributes timing to all cells via the packet, and every cell has its own path. Think about the redundancy built in with that, with fiber, right? This, again, this has been used in Metro. This has been used in a lot of 4G applications, most often used as a backup to GPS. So you have your GPS as your primary source, and then you have your PTP, your grandmaster, providing it through the network as your backup or your secondary. Why is that important? Because compared to 4G, what happens when you lost your timing in 4G? Switched over to holdover timing, right? Your site would go to holdover, and then it could maintain holdover well, depends on the type of clock source it has built into it. It wasn't as detrimental as it is for 5G, because in 5G, once you switch over to holdover, if that holdover isn't synchronized to the neighboring stations, do you have coordinated multipoint? No, you don't. You don't have TDD, and then you're in trouble. So I'm going to move away from synchronization now, and I'm going to move away from eCPRI and radio over Ethernet, and I'm going to finalize here on just the last couple of slides before our first break. This one has to do with the backhaul. How is the backhaul changing? Well, as Jeff and I will go into some of the applications later on, the biggest thing with backhaul, it's all about bandwidth. Not with eCPRI or radio over Ethernet, but just the sheer amount of user data. Think about all the over-the-air or the over-the-top applications, your streaming video, the idea moving forward, augmented reality and such. You know, I often joke about the next Pokemon Go, right? How many of you guys remember when Pokemon Go first came out on the phones, when that application first released, and networks were being dropped left and right just by the sheer number of users that jumped on Pokemon Go when it first came out? 5G is going to introduce a ton of new augmented reality applications, all of which are going to be high bandwidth. So what's going to happen with the next Pokemon Go, right? You move on, they're talking about changing these bandwidth, these networks. First of which is the data. We're starting to see our mobile backhauls upgrading to 100 gigabits per second, and in the not so distant future, 400 gigabits per second, just for the backhaul. Why are they doing this? Because they're going to be moving out. You're going to hear me use a new term. You see this on here, MEC, standing for Mobile Edge Computing. It's also called multi-access edge computing, depending on the circles that you're talking to. But what's the idea behind this? Well, think of your data center. As of right now, let's use the Pokemon Go application. If you had that in a data center located, that application is housed in either a colo or a data center that's far from the edge, it has to traverse that entire mobile backhaul in order to get there. That's taking up bandwidth. The idea of mobile edge computing is to taking those resources from the data center and moving them closer to the edge, as close to the edge as possible. Two reasons. First of which, latency between the two. Now, my end users that are all, let's say this is a city environment. Let's say it's a financial district. Let's take a stadium, for example, since we're right next to one. If I have that stadium full of 100,000 people that are all on Facebook Live streaming themselves that they're at the game, I don't want that traversing my entire network, taking up all my bandwidth. I want that going to a mobile edge computing as close to that location so it frees up all of my other resources and it doesn't tie up bandwidth. So you're seeing mobile edge computing moving closer to the edge, and the pipes that are feeding those mobile edge computings increasing up to 400 gigs. Does that make sense? And we'll go more into that later as well. Okay, so this is kind of summarizing this, and this is the question that I propose out here, is when we're taking what was traditionally in 4G, the BBU, and we're taking the functions of that BBU and turning it into logical entities, software, for the DU, where it can terminate my eCPRI and my IQ data, and I'm taking the other half of that and making it the CU, where it's distributing all of my user data out to the network. If that's software now, I can co-locate that. We talked about the 4 different locations and where I can co-locate those. The question becomes, where becomes my network demarcation point now? What is considered the RAN anymore? Because what you see here is that the RAN changes depending on where these elements are moved. Your entire RAN, in the case of the RU, DU, and CU for very tight latency requirements, could all be located all at the access point, and that could be your entire RAN. Or you could distribute those RAN functions across your access aggregation and even out to your core network. Now your RAN, NGFI, NGFI2, and mobile backhaul goes all the way back to the core. The strength of 5G allows for that flexibility. It gives you the ability to move those functions based on what your application is. The challenge becomes, well, where's my test point? Where is that demarcation point now? And again, Jeff and I will discuss that later on. Question?
Here in this diagram you have aggregation. Are you limiting the aggregation to websites that are used by the users? Or are you open to, let's say, somebody calling somebody else, a telephone call?
So make sure I understand your question correctly. When I state aggregation here, am I referring to that of website? No, so it consists of both. It'd be aggregation of combining multiple hardware devices. So this could be anywhere from taking multiple towers, multiple sites, and aggregating those over a single pipe in order to take advantage of that bandwidth. In traditional, if we looked at this back in 4G, this would be more of your backhaul versus your core here. But what we're stating here is at this aggregation point, although it was considered backhaul, so here's where you would have your CRAN hub, depending on where you put those functions, that's no longer just dedicated to that CRAN hub. That functionality, that aggregation, if you did in this site, could be done at the access point, or it could be done here at the edge point, depending on where I put that distributive and centralized unit function. So it's not pertaining specifically to user traffic necessarily. It's more of network design. Where do I want that traffic to go? Yes, sir?
What's the concept of elastic RAN? Is that the same concept?
That's a good question. So the question was, how does this relate to elastic RAN, right? Where that term was being used very popularly. This is the same. This is the same functionality of being able to take that RAN and break it up, subdivide it into its logical functions, and then put those in the network elements where it would be the most beneficial. And we'll talk about that later. But yeah, same concept. Yep. Question?
MEC in place, isn't there going to be another mid-haul from the MEC to the core?
I'm sorry, with the MEC in place, can you say that again?
Is there going to be another mid-haul, like front haul, back haul, and mid?
Yeah, so the question was when the MEC, when you put the metro or mobile edge computing aspect into this image, be it depending on where it would go based on the application, what would that communication, would that also be a connection from the MEC back to the core, or would that be considered a mid-haul? That would be, and again, it depends on where the size of that mobile edge computing would be and the location, but yeah, best example would be mid-haul. Absolutely, the NGFI 2. And the two reasons behind that, first which, the NGFI 2, and I'll go into this a little bit more, is that it has less latency requirements than NGFI 1. NGFI 1 is much more strict with latency, where you want that, depending on what that application is, that would determine where your MEC would go. But once it left the MEC back to the core, that would be your mid-haul. Less on a latency requirement, higher in bandwidth requirement. Other questions? These are great questions, by the way. Thank you.
Basically, you're saying that if you have a division of the functions into a mid-haul, then you don't guarantee any latency.
I wouldn't say you don't guarantee latency. It's just a different latency requirement. You're looking at much more relaxed latency requirements for those applications. And when I say that, and I have slides later on more on this. Actually, do I have that? Actually, it's the next slide. So going back to your question, the question was, once I go from my front haul to my mid-haul, is it because my mid-haul would have less of a latency requirement? There's no latency requirement. And the answer is it's not no latency requirement, it's just less. So what I identify here is that depending on the standard, and these are 3 different standards, but all of them are referring to different latency values per that aspect of the network. So 3GPP, IEEE 802.1cm, and then 1914.1. And what you'll see is URLLC, ultra reliable low latency communication. Ultra reliable low latency communication. That is your V2X traffic. Always the tightest latency requirement. Now, look at EMBB, enhanced mobile broadband. That's your streaming 4K video, right? Or augmented reality. Higher bandwidth. Less requirement, more relaxed, 1 to 3 milliseconds here, 4 milliseconds. So going to the question that you asked earlier, depending on if I'm at the mobile mid-haul, let's take the bottom example here, where you see NGFI 2, that's 1 to 3 milliseconds of latency one way, versus NGFI 1, you're looking at 50 to 100 microseconds. Much tighter. So where I place my DU and CU functionality is largely dependent on which applications I'm supporting and their latency requirements for each. So in the case of ultra reliable low latency communication with a 50 microsecond one-way latency, that's tight, that's very small. I need to have that DU functionality either co-located to my radio unit or in the radio unit itself. That's your V2X application. Versus my enhanced mobile broadband, that's 4 milliseconds for my device, my UE, all the way back to my next generation core. I can have that traffic go all the way over here because I got more space to deal with, more latency. I don't have to terminate that here. I can have that done here. That would be where my metro edge or mobile edge computing would be. Does that make sense?
So you're talking about the difference between an autonomous car or an offsite surgery versus a mall or a stadium versus whether...
Exactly. 3 different applications, 3 entirely different requirements. But if they're all going to the same radio, how are they treated, right? I can differentiate those and make sure they go to the proper resources and use the requirements. For example, as I mentioned earlier, the most expensive, having it co-located, is dedicated to that mission critical data, that high latency sensitive data. Versus my weather monitoring, I can send that down the pipe. And I can differentiate those. Whereas in 4G with LTE, I couldn't do that. Antenna container is an antenna container, they were all treated equally. It's like boarding a train, right? No passenger is more important than another passenger. Once you're on that train, you're on it until the end of the road. Versus, in this case, it's more of an example of cars, emergency vehicles. You take your own vehicle, you get on the expressway, if there's an emergency vehicle that comes by, you move out of the way, you let them pass, well, supposedly. Doesn't always work that way in Chicago. Yep.
Do you handle wireline telephones in this kind of configuration?
No, wireline telephones handle this a little bit differently. That's a different network topology.
So you don't consider them at all?
I wouldn't say I wouldn't consider them, because once they get out of, because we're discussing specifically just the NGFI 1 and NGFI 2 here, once you get past the mobile backhaul into the core, then you're definitely integrating that with IP, or it could be anything from voice telephony, it could be anything from data streaming and so on. Then there's different differentiators there that are prioritizing that traffic. But what we're specifically referring to is just the over-the-air traffic from the radio to that once we get it to the core. Good. Yeah, Tom. I already told you can't ask questions today, Tom.
You set that traffic up in advance, or is it done dynamically? The traffic type?
From when it's terminated on the radio?
Gentleman had 3 applications.
Mm-hmm.
They're all flying out there.
That's okay. So that's you always ask the loaded questions. Okay, so in the initial rollout, that's going to be programmed statically, right? They're not going to be doing it dynamic yet. The goal is to get to dynamic bandwidth allocation, which is an application Jeff and I can touch on a little bit later, but that's future thinking, right? Because the aspect that we haven't discussed in this, which will be in a later presentation, software-defined networks and network functionality, or network virtual functionality. I can never say that right. Network NFV, yes. The idea behind that is having an orchestrator that can dynamically allocate that bandwidth based on traffic changes, right? Because that, not only is there different priorities of traffic, but you also have different time of day, right? Let's say the stadium, right? You're only going to be using the stadium so many times out of the year where it's going to be requiring that bandwidth. But do you want to dedicate all those resources to the stadium if it's not being used every day? You want to be able to identify what other business districts can also take advantage of that when the stadium's not using all that bandwidth. That's the dynamic bandwidth allocation.
Network slicing.
Network slicing, absolutely. And that we'll get into later.
So right now it's being set up as design functionality for whatever the location is.
Correct. Yeah, in the initial stages right now. Yeah, absolutely.
So when you think about the network deployment, are you looking at the optionality of everything having it up front, and then you have the option to have your units in various locations?
So that's a good question. When we're talking about, so the question is right, the question was, are we setting it up, are you provisioning the network today to be able to support these future dynamic allocations, right? The different applications that we've been discussing. In the initial release right now, we're looking at, and then when I say initial release, I'm talking about 3GPP release 15 as it is today. The number one application that's addressing is enhanced mobile broadband. So when you see the commercials and the discussion right now, it's all about being able to have that higher uplink and download speeds or downlink speeds to your device itself. In that application, that's what the networks are primarily supporting today in initial 5G rollout. In release 16, and there's debates as to when release 16 is going to be coming out, but we're going to say optimistically within the next 6 months. That's going to be the full rollout of 5G, which you have to have the support of not only the enhanced mobile broadband, but the additional applications that we described, and being able to support each one individually and simultaneously. So in the 5G that we've worked on today, we haven't seen a lot of integration in the 5G rollouts or the sites, we'll say field trials, that are supporting multiple applications. They're pretty dedicated to that specific type of application that they want to support. So in the case of, as I mentioned, enhanced mobile broadband, it's all about download speeds. In the case of, we've seen isolated V2X applications where it was vehicle platooning. If you're not familiar, are you guys familiar with vehicle platooning? I was going to say, because we actually seen that out here first as one of the first stages of that. That's what one driver is driving a truck, but the other trucks that are following it are all being controlled by that one driver. They're basically platooning, one driver, 3 trucks, and it's using a combination of communicating over the air with the network, GPS location, as well as RF between the first truck and that of the remaining trucks. So it's a pretty neat application. Did it answer your question?
Yeah.
Okay. Okay. You know what? We're running out of time here, and I'll just briefly touch on the core side. But this is basically, as we were just talking about, as we move the MEC, the mobile edge computing, closer to that of the edge, we're starting to see the increased bandwidth demands over the metro and core network. This is where we're starting, again, seeing how do you interconnect, and this is the question about the mid-haul. How are you interconnecting multiple mobile edge computing stations or computing locations? That's where you're seeing bandwidths and wavelengths up to 400 gigabits per second over your DWDM ring. We're involved in that testing today. That's being done by different groups, though. You're starting to see new players in this space because of the idea of having, in essence, a field data center, right? Now you're not talking necessarily about co-locations, nor are you talking about enterprise data centers. You're talking about field ruggedized, independent cabinets of data racks, of data centers, of individual servers, all of which connecting through a fiber network, serving a geographic location, depending on what that requirement is. That's being driven, again, by latency. How long does it take for that application to get there? As well as bandwidth. How much data do I need to pipe through that specific server or that specific location? So the test requirements that we've seen there, you're seeing, again, up to 400 gigabits per second. We're also seeing quality of service measurements. As we differentiate these services, are the ones that have the highest priority getting to my mobile edge computing and getting out from my mobile edge computing in the amount of latency that we're expecting. And then, depending on in the core network, we're starting to see G.709 or OTN, Optical Transport Network. We're starting to see that protocol being used, pushed again closer out to the edge to manage these different types of traffic profiles. So what does this all mean? Again, as we go through the presentations, you're going to see that as we move from 4G to that of 5G, we're going to go away from CPRI and go more into a packet-based transport. Once we move to the traffic-based or packet-based transport, we get the flexibility to start differentiating those individual services based on their different requirements that I showed in the previous slides, latency requirements, synchronization requirements. Moving forward to today, Jeff and I are going to be discussing how those changes are affecting both over-the-air measurements and how we do them today, as well as how we do the transport and optical measurements over the network. All right?